Hello, in this video I'm going to explain prime factorization and the greatest common factor, or GCF, same thing. All right, so problem number one here, it says identify the number as prime, composite, or neither. Now we did this a little bit in the last section, M1.7 I believe it was, the last video. So this is a continuation of that concept. All right, so we have 125. Now, one thing we can do is to look to see if 125 is on this table of prime numbers. It's not only because this cuts off at 100 or so, 97. So we got to find a different strategy to determine if this is prime, composite, or neither. So basically, we have to ask the question, can 125 be broken down into factors other than 1 and 125? And here is where the divisibility rules come into play. They're really helpful, and here's another example of where knowing the divisibility rules is going to make things easy. So we have 125. Now, we could look at the number 2 in using divisibility rules and ask if 2 goes into this. Well, this is an odd number, so 2 will not go into it. We could look at the number 3 by adding the digits, right? Recall that. To see if a number is divisible by 3, you sum the digits. 1 plus 2 is 3, 3 plus 5 is 8, and 3 does not divide into 8. Being that this is an odd number, all even numbers will not divide into it. We can skip 4. How about the number 5? Yeah, see, this ends in 5. So if a number ends in 5 or 0, we know 5 goes into it. So this can break down into 5 times what equals 125. Well, 4 quarters will give us $1. 1 more quarter, 5 quarters will give us $1.25. So remember, you can use the money analogy to help you with some of these larger numbers. Sorry, so that should be 25, right? That should be 25, right there. 5 times 25 is 125. So the fact that we could break this number down into other numbers besides 1 times 125 tells us that this has to be a composite number. Okay, it has to be a composite number. So let's try composite, because there are other factors besides 1 times 125. And here it is right here. 5 times 25 is 125. Now, they're asking for something that's called prime factorization. So this is going to be something that you'll be doing quite a bit of in this course and also in Math 50. There are various ways to determine prime factorization. And one of the easiest ways is to use what's called the factor tree. You might have used it before. You might have looked at it or seen it before. And here generally is how it works. Let's do a simple problem first, and we'll come back to this 125. Let's use 12 and pretend the instructions say use the factor tree to find the prime factorization, or to just find the prime factorization, and you decided to use the factor tree. So we got to determine the factors of 12, but not 1 times 12, because that does not help us, right? We need other factors besides 1 times 12. Well, we got a couple of choices. We can go with 6 times 2 or 4 times 3. It doesn't matter, actually. You're going to get the same answer as a result. So first, let's try 6 times 2. So these little things here are branches of a tree. That's what these represent, branches of a tree. and you're going to keep breaking down a number. This is a composite number because it can be broken down into other factors. So any composite number that remains on a branch tree, you want to keep breaking it down. But any prime number that cannot break down anymore, you circle it because we're done with that tree. It's finished with that branch. That branch is finished. Okay, so let's look at the number 6. What times what is 6? And we know that 2 times 3 is 6. 2 is a prime number because that cannot break down anymore. And 3 is also a prime number. There it is. So once you reach to the point where all you have are just circled numbers which represent prime numbers, then you're done doing prime factorization. Now, the way you would want to write this out and type it in the computer would be this way. You can start with the lowest numbers, which are 2 2's. So you got 2 dot, which means multiplication, right? 2 dot 3. So we have 2 2's, here they are, and a 3 with a multiplication dot in between all of these because factorization implies that you're multiplying numbers together. These are factors of 12. In fact, if you were to multiply these out, you better get 12 back, and we do, because 4 times 3 is 12. So that's how you perform prime factorization using a factor tree. Now, let's try something else since we're on that topic here. Let's pretend we didn't want to use 6 and 2, but we want to use 4 and 3. We still get the same thing? Well, let's find out. Now, 3 is a prime number we cannot break down, so we can circle it. 4 is composite because it can be broken down into 2 times 2, and 2's are prime. And look, it's the exact same thing. So the nice thing about the factor tree is that it does not matter which numbers you choose for the branches, you'll wind up with the same prime numbers at the very end. All right, so that's the concept of using the factor tree. So let's go back to our original problem and see if we can figure it out. So we have 125. What times what is 125? So, and by the way, this little point here, this is a branch. It does not point to the 2. Okay, so some people have made that mistake. No, this is just simply a branch that's coming off this base. This is the base of a tree. These are branches coming out of it. I'm not pointing to the 2, just so you know. So this number ends in 5. So guess what? I know 5 goes into it for sure. It's divisible by 5. 125 is divisible by 5 because it ends in 5. So I know that 5 times something is 125. I also know that 5 is a prime number. I'm going to circle it. Now, the work we did earlier, we know that 5 times 25 is 125. So now we got to ask ourselves, is this a prime number or a composite number? And the fact that this ends in 5 tells us that, again, 5 goes into it. In fact, 5 times 5 is 25, right? Now, we got to the point where each branch of the tree is finished because it has a prime number at the very end. Therefore, we're done with prime factorization. So you would type in the computer 5.5.5 because 5 times 5 times 5 is 125. So we got 5, and then here's the multiplication dot right here. Don't use the decimal dot. So this is in prime factorization format. All right, so here we go. Let's see if we can go a little bit swifter this time. Now, that's a huge number. You're not going to see that big of a number in Math 50. But for some reason, in Math 25, they gave you huge numbers. Congratulations. All right. So this is going to be a biggie, right? But remember, as we go down the tree, the number is going to get smaller. 1155. What times what is 1155? I have no idea. However, this ends in 5, so I know for sure that 5 times something is 1155. So I circled the 5 because it's a prime number. Now, how do I know what 5 times this is to give me 1155? We're going to do the opposite, the inverse of multiplication, which is division. We're going to divide 5 into 1155 to give us this. So quick and dirty, nothing fancy here. So this should be a review for you, right? $231. 5 times 231 is 1155. All right. So as you can see, we went from 1155 down to 231. So significant drop off. We dropped off by a factor of 5. Okay. Now the question is this a composite number or a prime number? What times what is 231? I have no idea. But I'm going to use the divisibility rules to help me. So let's start with 2. Now, this ends in 1, which makes it an odd number, so 2 will not divide into 231. Let's try the divisibility rule for 3, which means add the digits. 2 plus 3 is 5, 5 plus 1 is 6, and 3 goes into 6. Oh, good. Goody. 3, which is prime, times something is 231. Again, I'm going to divide 3 into 231 to find out what this number is. Quick and dirty, nothing fancy. Oh, 3 times 77 is 231. All of a sudden, this is manageable. It's not too bad, right? Now, is this a prime number or a composite number? Well, this number here is on the multiplication tables, and by now, you've mastered them, right? Correct. 7 times 11 is 77. 7 is a prime number. 11 is a prime number, and you've also mastered these, right? All the way up to about 50-ish or so, 40-ish. All right, so there it is. So let's start with the smallest number. 3 times 5 times 7 times 11 is the prime factorization of 1155. So first, let's answer the question. Yes, it's composite because we can break it down. See that? We got other factors besides 1 times 1155. What is the prime factorization? Three dot 5.7.11. That's what it is. Oh, this seems relatively easy. All right, 84. 84. Now, you can pick any number you want as long as it's not 1 times 84. if you notice that this is an even number, and I know 2 goes into an even number, so if you say 2 times something, it's not like you're wasting your time. It's not like, oh, I could have picked a bigger number. It doesn't matter, because in the end, it's going to be this. You're going to have to pick 2. 2 is going to be part of that factorization, guaranteed. In fact, there could be more 2's. So 2 times what is 84? Well, let's think about it. Let's cut 84 in half. Let's divide 84 by 2. So 84 cut in half is what? 42. Good. Now, what times what is 42? Again, you can pick 6 times 7. You can pick 2 times 21. It doesn't matter. You still get the same number. Let's try 6 times 7 just for fun. 7 is a prime number. Here we got 2 times 3. Done. So 2.2.3.7. There's our answer. It's definitely composite. And the factorization is 2.2.3.7. And we got another one. $147. Now this might look familiar because we tackled this number in the last video, I believe it was, in a recent video. So is this a prime number or a composite? It's odd. It doesn't mean it's prime though. So this is an odd number, so we're not going to try any even number. We know no even number divides into an odd number. Okay, so we're going to skip the evens. So let's go to the next number, prime number, or number for divisibility, and that's the number 3. So let's add these. 1 and 4 is 5. 5 and 7 is 12. Aha. So 3 times something is 147 because of the divisibility rule, right? 12 is divisible by 3, so 3 goes into 147. Now, quick and dirty, nothing fancy. Aha, 49. 3 times 49 is 147. And using your multiplication table knowledge, you know that 7 times 7 is 49. So we have a composite number. And the prime factorization is 3.7.7. Well, here's a nice big one here. All of a sudden, they throw this big number at us. Lucky for us, we know our divisibility rules, right? Correct. So, 567. What times what is 567? Not a clue. Odd number, all even numbers do not go into it. So let's try the number 3 by adding the digits to get the sum of the digits. 5 plus 6 is 11. 11 plus 7 is 18. And 3 divides into 18 evenly with no remainder. Aha. 3 times something is 567. 3 is in a 5 once. 3 is in a 26. 3 is in a 27. 189. Nice. All right. So now is 189 composite or prime? Let's try divisibility rules again. 1 plus 8 is 9. 9 and 9 is 18. Yeah, 3 goes into it again. Nice. Very good. So 3 into 189. 3 goes into 18 6 times. 3 goes into 9 3 times. Very good. 3 times 63 is 189. Is 63 prime or composite? And you said composite because a bunch of different ways could be gotten here, but 7 times 9 from the multiplication table we know is 63. And then 9 is the same as 3 times 3. So we have 4 3s and a 7. There it is. So the prime factorization of a number is the DNA of the number. Every number has a distinct DNA, a different prime factorization. Pretty cool, right? Anyway, so we have a bunch of 3s here. All right. So we're still going to find the prime factorization, but the only difference here is that they want us to use exponential form for repeated factors. So for example, let's take a look at this one here. We could write this out as 3 to the 4th times 7. These are equivalent expressions. Remember, this is the base, that's the exponent, and the exponent tells us how many times the base repeats or multiplies by itself. We have 4 copies of 3, the base, and that's what this is saying, 4 copies of 3, the base. So after we do this problem, they want the answer in this format, exponential format. That's the only thing that's different about this problem. All right, so let's erase this and try the next one. All right, so what do we got here? 126, not too bad, right? Even number, guaranteed 2 divides into it. Two goes into 12 6 times, 2 goes into 6 3 times. Nice. Quick and dirty. 63 you said is 7 times 9, correct? 3 times 3. So let's write this out in exponential format. So let's start with the lowest number, 2 dot, we have 2 3s, so 3 to the 2nd power dot 7. So let's see which one matches. Is it A? Nope. Is it B? B looks like the winner, right? Looks like we got B. Well, here's a real easy one. I think you know the answer already, right? So we got 9, 3, 3 primes. They want the answers with exponents for repeated factors, and we have a repeated factor because we have 2 3s, so we have 3 squared, or 3 to the 2nd power. We have 2 copies of 3. So you type in the base 3, and then you type in this exponent symbol down here, the superscript, click it, and then you'll be able to type in the 2. All right, so more practice. Find the prime factorization of 52. Use exponents for repeated factors. Let's bang this out. So let's see, 50, right? 25 times 2 is 50, which means that 2 times 26 is 52, right? Yeah. Half of a deck of cards is 26. What times what is 26? And you said 2 times 13, correct? 2 is prime. Is 13 prime? Yes, you said, correct. So we have 2 2s times 13. And then you can, once your cursor's in the exponent here, just simply right arrow to bring it back down, and then you can type in the dot 13. Now here they don't tell us anything about using exponential form, so we have to assume they just want the dot version all the way through, the prime factored form without any exponents. 225. This 5 is staring right at me. I know for a fact 5 times something is 225. I just don't know what that is. I'm about to find out. Quick and dirty. Nothing fancy. 5 times 45 is 225. And then you said that, oh yeah, 45, that's the same thing as 9 times 5. Correct. Circle your primes. Our final answer in factored form, 3.3.5.5. They don't specify exponential form, so we have to assume that's what they want. Let's try it, see what happens. Nice big number. Find the prime factorization. Doing this now in Math 25 is going to really help out in Math 50. You'll see. It's well worth the effort. So there's a bunch of different ways we can break this down. To me, one of the most intuitive ways is to say, you know what? I know that 5 times 100 is 500. Boom. Now, again, we have multiple ways to do this. And again, one easy way is to say, I know 10 times 10 is 100. These are both composite. And I know that 2 times 5 is 10. I know that 2 times 5 is 10. And we're done. See that? In about 10, 15 seconds, we broke this down. And you followed right along. So we have 2 2s, 3 5s. All right, so let's put that in there and see if it works. All right, we're about to switch gears here. So I think you got the hang of the factor tree technique to find prime factorization. So we're about to switch gears. Here we go. There's something that's called greatest common factor. So the greatest common factor is the biggest number that divides into two or more other numbers. So let me give you a smaller example before we dive into this thing. All right, so let's say we have the number 8 and the number 12. What is the biggest number you can think of that divides both into 8 and 12? That number is 4. 4 is the biggest number possible that divides evenly into 8 and 12. That's what's called the greatest common factor, the biggest number possible that divides into all, both. There could be more than 2 numbers given, but in this case, in this example, it's just 2 numbers. So so that's in general what it means, okay? Greatest common factor is the biggest number that divides into 2 different numbers. I'll explain more as we do this particular problem. So let's dive into this problem here. Now they give you a nice big number here to deal with. So we have 189 and then we have 441. What times what is 189? 3 goes into this, right? 3. This is divisible by 3 using the divisibility rules. 1 plus 8 is 9. 9 and 9 is 18. 3 goes into 18. And we just did that earlier. Can't recall what that is, so we got to quickly do this here. 3 goes into 18 6 times. 3 goes into 9, 63, we said. So we're going to break down. We're going to do the prime factorization of both numbers, and then we'll take it from there. Then we'll have to do some other step. But for right now, let's just do the prime factorization for both numbers. That's what I'm doing here. So I'm going to write these down in exponential form. Not that it matters, but I'll just do that. So this is the prime factorization of 189. We got to do the same thing with this. Now notice that using the divisibility rules, we can also say that 4 plus 4 is 8, plus 1 is 9. So 3 goes into 9. Guess what? 9 goes into 9 too. Because remember, 3 and 9, we could have used 9 here too. 3 and 9 have the same rules. I'm going to use 9 just for fun. So I know 9 times something. I just don't know what that other thing is. So I'm about to find out. 9 goes into 44 4 times. 4 times 9 is 36. Remainder is 8. 49. 9 times 49 is 441. And I think we can deal with it in our heads here from our knowledge of the multiplication tables, correct? Yes, you said. So let's write these out in exponential form. We have 3 to the second power times 7 to the second power. All right, so we did all that work. Now what? Now, it might help if we just quickly look at the help here. Let me just show you something. See where it is. There's this very long sentence that might sound confusing when you read it. And I would highly recommend, by the way, that you look at the help and get familiar with the verbiage used in math, because it's really going to help you out. It really will, to be able to be familiar with it. And this is it here. Here's the verbiage right here. The greatest common factor is the product of the common prime factors, the common prime factors in which the exponent is the smallest powers, the smallest power. I kind of summarized this for you. So that's what this tough looking sentence in help says. That's how you determine the greatest common factor. You have to look at and compare the exponents of common factors. So these numbers, the bases have to be in both. Okay, so the base has to be in both. If the base is not in both, it cannot be part of the greatest common factor. So let's look at this. All right, so the key here is smallest power, smallest power. So let's look at the threes. We have 3 3s here, right? We have 2 3s here. This is the smallest power. So this comes down. So greatest common factor, GCF, also known as GCF. So it's abbreviated a lot. Get comfortable with GCF, greatest common factor. So what we're bringing down here to compute this GCF is this one. Why this one and not that one? Because the rules say so. That's why. It's the smallest power, right? 2 smaller than 3, so this comes down. Then we move on to the next number. So, and by the way, if there's nothing up here, if there's no exponent here, it's really assumed to be 1. So an exponent of 1 or nothing at all is the same thing. So here we have 1 7, and here we have 2 7s. So this one here is smaller, right? Smaller, so the 1 7 comes down like that. Now that we did all that, what we really have to do, see what they want is they want the final answer here. They don't want you to type that in there, even though it's almost correct. They want the number. So all we got to do now is just figure it out, all right? Just multiply it out. Well, we know that 3 to the second power is the same as 3 times 3. So this is 9, right? That's 9. 9 times 7, you said, is 63. Correct. So 63 is the greatest common number that divides into both 189 and 441. So let's try 63 and see if that works. So here they're giving us 3 numbers. It doesn't matter, it's the same technique. And remember, this is one way to do it. There are other ways to do it. In fact, later on, we'll do a different technique. But from right now, let's use this method. So let's write out our prime factorization. Now, another way you can do this is this way. You can use the factor tree, and that's fine. But these numbers are on the small side. So you know what I'm going to do instead? I'm going to use my knowledge of the multiplication table and break this down into prime numbers. 28 is the same as 2 times 14. 14 is the same as 2 times 7. Done. These are all primes. 20. Remember, we want primes here. So start with 2. 2 times 10, start with 2 because it's an even number. 2 times 10 is 20. And then 2 times 5 is 10. Got all primes? Done. 24. 2 times 12 is 24. 2 times 6 is 12. 2 times 3 is 6. If you don't want to do that technique, you can just simply use the factor tree as I did earlier. Nevertheless, we need to break these numbers down into its prime factorization. We've done that. Now we're going to use that same logic that we used earlier. Remember that sentence, that long sentence? It's going to apply here. So what do we have here? Let's break this down using powers. We have 2 squared times 7. Here we have 2 squared times 5. Here we have 2 to the 3rd power times 3. So let's start with the 2's first. Remember, the rule says the factor with the smallest exponent, smallest power, comes down. So GCF. Let's start to build the GCF. Well, we have 2 of them that have the power of 2. One of them has a power of 3. So the smallest power between all of these is a power of 2, correct? This just simply has an extra power. So 2 to the 2nd power comes down. Now we look at what's left here. We have a 7, a 5, and a 3. And remember, for the greatest common factor, the factor has to be in all the lists, right? We have a list here, but we don't have anything that's common to all. We have a 7 here, a 5 here, and a 3 here. There's no number except 1, which doesn't help us, that's common to all. So we cannot bring any of these down. So really, this is, right here, the greatest common factor. And what is 2 to the 2nd power? Well, 2 times 2 is 4. And that makes sense, right? 4 is the biggest number possible that divides into all these. Let's try 4 and see if it works. Okay, more GCF fun. You'll run into this in Math 128 if that's the path you're going to take for your major. You're not going to see this in Math 50. Interestingly enough, it's good to know. So why not take advantage of it now? So let's use the factor tree here just for a little bit of change. So 27, 8, 2 different trees, right? So let's put a little barrier there. 3 times 9, 3 times 3, 2 times 4, 2 times 2. Here we have 3 to the 3rd power. Here we have 2 to the 3rd power. So the question is, and remember, we're not looking at the powers for this. We're looking at the base, right? These are the numbers we want to see. Are they common? Not if the powers are common, but if the base is common, the number that we're interested in. So there's a 3 here, there's a 2 here. They're not the same. They're not common. Even though the powers are the same, it doesn't matter. We care about the base, the number down here. So whenever you have a situation where you don't have a number that's common to both at all, we can say that the GCF, the greatest common factor, really is 1, because 1 times anything is that number. All right, so see that? 1 times this is this, 1 times that is that, and 1 is common to both. So so the greatest common factor is 1. All right, now we're going to do a different technique to find the greatest common factor. And this technique is called dividing by prime factors. So if you want to, if you like it, you can use this, or you can use the factor tree that we've been doing. They just put it in here as an alternative way to find the greatest common factor. So here we're looking at 210 and 350. So we're going to have a strange notation here. So here's what it looks like. We have 210, 350. You're going to put these in an upside down division box. And then what you're going to do is you're going to divide by prime numbers, and you're going to go downwards. All right, now start with the smallest prime number. And the smallest prime number is 2. And the fact that these are even numbers, 2 certainly goes into both. So the number you choose here has to divide evenly into both. And the number 2 divides into both. Now, just for the sake of expediency here, I'm going to see if I can do these in my head. Hopefully I can do these in my head here. Or you can use long division. Half of 210, right? We're dividing by 2. Half of 210 is 105, correct? 105. Half of 350 is 175, just to save a little time here. And you can do the division on the side if you like. 350 divided by 2 is 175. So now we're right here. Again, you put these in a reverse upside down division box. And then you ask yourself, what's another prime number that divides into both? Well, 2 is out of the question because these are odds. Okay, so if one or the other is odd, 2 is not going to work. Can 3 work? Let's use the rules of divisibility. Yeah, our favorite topic here. So 1 plus 0 is 1. 1 plus 5 is 6. That works. 1 plus 7 is 8. 8 plus 5 is 13. That doesn't work. 4 is out of the question. How about 5? Well, this ends in 5. This ends in 5. No doubt about it. 5 divides into both of these evenly. All right, so let's see here. So 5 times 20 is 100, but this is 1 more 5. So 5 times 21 is 105, all right? Now, 175 divided by 5. Let me just bang it out here. $35. All right, we're moving down the list here. So now we have 21 and 35. And now we have to ask again, is there a number that divides into 21 and 35? And the number I'm thinking about is 7, right? 7 does. So 7 divides into 21 3 times. 7 divides into 35 5 times. Now we're down to here. Now we're down to here. Before I put the upside down division bar, let's think, is there a number that divides into 3 and 5? Well, these are both prime numbers and they don't break down. All of these were composite numbers. That's why they broke down. These are prime numbers. They don't break down. And it's not the same number. So, no. I mean, you can say 1, but 1's not going to really change anything, right? 1's not going to make any difference. So what happens is this now. All right. So the list on the side, all these prime numbers here, all of these, when you multiply all of these, you're going to get the GCF. So GCF is going to be 2 times 5 times 7. Now remember, so you might be thinking, well, what about these down here? Think of these as leftover numbers, okay? Because there's no common factor. Notice that these numbers here are common. 2 is common to this, 5 is common to that, 7 is common to that. There's nothing common to that. 1 is, but again, 1's not going to help us. So these are leftover numbers. So these are the common numbers, the greatest common number between 210 and 350. So what we got to do now is multiply this out to get our answer. 2 times 5 is 10. 10 times 7 is 70. So 70 appears to be the greatest common factor. All right, so this division by primes, again, it's good to know. You don't have to use it, but it could be as effective as using the factor tree. It's your choice. Okay, we have one more, and it doesn't specify which technique. Let's go back to the factor tree. So we have 189. We have 441. Not easy numbers. So let's think about this. 1 and 8 is 9. 9 and 9 is 18. I know 3 goes into 18. I also know 9 goes into 18. So either choice works using divisibility rules. All I got to do now is divide. Well, let's see. 9 divided in 18 is 2 times. 9 divided into 9 is 1 time. If you're not sure what I did, don't worry about it. Use long division. Okay. But that's one quick way to do it. This breaks down into 3 and 3. This breaks down into 3 and 7. All right. So here we got this. And again, we got 4 plus 4 is 8 plus 1 is 9. So again, 9 goes into this. Now, this is tougher than that, so I'm not going to do it in my head. I'm not going to try, so I'm going to just simply do it this way. Why does this number look familiar? I'm not sure. I think we've seen it before, right? 9 goes into 44 4 times. 4 times 9 is 36. Difference is 8, 81, 49. I think we did this before, so I guess we'll do it again. All right. Now we can do this from our recall of multiplication facts. 3 and 3. 7 and 7. Let's change these to exponential form. We got 3 to the 3rd power. We have 3 to the 2nd power. 7 to the 2nd power. What's the GCF? What do you think? We got 3 3s here. We got 2 3s here. Remember, the rule is the smallest power wins for the GCF. So this comes down. We have 1 7 here. We have 2 7s here. There's fewer 7s here. So 7 to the 1st power, or just 7, comes down. And then we got 3 times 3 is, remember, 3 to the 2nd power is the same as 3 times 3. And 3 times 3 is 9. 9 times 7 is 63. So 63 is the greatest common factor. All right, so a lot of information in this video here, and some of the concepts are definitely, fairly heady here. You'll see the greatest common factor in Math 128, but not in Math 50. So they threw it in here just for fun, I suppose. Still good to know. So that's how you perform prime factorization and the greatest common factor. If you like my content, click on the like button, post your comments below, and subscribe to my channel. Thank you for watching.